About 4.5 billion years ago, amid the chaos of the early solar system, Earth was a blazing sphere of molten rock covered by churning magma oceans. It was a planet filled with toxic gases and magma, yet somehow life was able to take root. Geochemical evidence shows that the earliest traces of life appeared around 3.8 billion years ago. With no oxygen to breathe and no sunlight, life emerged in the darkness of the deep ocean, around hydrothermal vents where chemical energy replaced light. Beginning from simple single-celled organisms, life started a long evolutionary journey. As the atmosphere changed, the planet nearly froze on a global scale. Life repeatedly stood on the brink of extinction. And then, unexpectedly, the Cambrian explosion unfolded, when life diversified into nearly every form imaginable. This is a journey into prehistoric Earth, where we will explore how a chaotic planet gradually became the only living world we know. Earth during the hadean Eon, a name derived from Hades, the underworld in Greek mythology, was a world nearly impossible to inhabit. At that time, the surface was a glowing ocean of magma, constantly disturbed by intense volcanic activity, asteroid impacts, and solar radiation far stronger than today. The primordial atmosphere was a toxic, reducing mixture of carbon dioxide, methane, ammonia, and hydrogen sulfide. Oxygen, the element closely associated with modern life, was virtually non-existent. Meteor bombardment occurred at high frequency, especially during the period known as the Late Heavy Bombardment around 4.1 to 3.8 billion years ago. Then, Earth began forming its first solid crust. The oldest minerals ever discovered, zircon crystals, about 4.4 billion years old, show that parts of the surface had cooled enough for liquid water to exist locally. So where did water come from on a world once a sea of fire? Modern science suggests a large portion came from internal degassing, as water vapor was released from magma and condensed as the planet gradually cooled. The boundary between the hadean and the archean marks a fundamental transition. The archean, beginning around 4.0 billion years ago, was still a harsh era, but stable enough for more complex processes to unfold. The most striking evidence comes from ancient carbon signatures in sedimentary rock layers in Greenland and Canada. Scientists discovered unusual carbon isotope ratios of C12 to C13 dated to about 3.8 billion years ago. Increasingly, models show that life could emerge under extreme conditions, especially in environments isolated from the chaotic surface. One key candidate: deep sea hydrothermal vents on the ocean floor. Here, seawater penetrates deep into the hot crust, reacts with metal-rich rocks, and erupts back as chemically rich superheated fluids. These environments provide stable chemical energy, catalytic minerals, and microscopic structures, ideal conditions for prebiotic chemistry. More importantly, early life did not require sunlight, oxygen, or an atmosphere like today's. It could form in permanent darkness under high pressure, where the surface no longer had direct influence. Once water stabilized and primitive life took hold, the primordial oceans became the main stage for Earth's greatest experiment, where life not only survived, but began learning to sustain itself. Around 3.8 to 3.5 billion years ago, most of Earth's surface was covered by water. The oceans at that time were dark in color, rich in dissolved iron, warmer than today, and constantly stirred by tectonic activity and hydrothermal vents. In return, however, they offered something priceless: relative stability. The earliest living organisms were bacteria and archaea, remarkable because they can survive conditions most modern life cannot tolerate. Temperatures above 100 degrees C, extreme salinity, crushing pressure, and environments completely devoid of oxygen. Many biologists consider archaea fossils at the physiological level because their metabolic pathways are closer to early life than any other surviving group. One of the clearest pieces of evidence for ancient life is stromatolites, layered rock-like structures created by microbial communities. The oldest known stromatolites date back about 3.5 billion years, and remarkably, they still exist today in certain shallow waters, such as Shark Bay in Australia. These structures are not individual organisms, but records of collective cooperation. Microorganisms trap sediments, bind minerals, and gradually build thin layers over time. Of particular interest is the RNA world hypothesis, which suggests that RNA molecules capable of both storing information and catalyzing chemical reactions may have been a crucial intermediate step before the emergence of DNA and proteins. These reactions did not require sunlight, but instead relied on chemical gradients in seawater and minerals on the ocean floor. Crucially, early life did not require oxygen. Instead of oxygen-based respiration, primitive organisms extracted energy from chemical reactions, such as the oxidation of hydrogen, sulfur, or iron. In other words, the first life did not breathe but metabolized its surroundings through slow, subtle chemical exchanges. From a survival perspective, this was a wise strategy. Sunlight at the time carried lethal levels of ultraviolet radiation due to the absence of an ozone layer. On land, radiation could destroy organic molecules in a very short time. Beneath the ocean, especially at great depths, water acted as a natural shield, allowing the fragile structures of early life to persist long enough to replicate and evolve. And once that happened, this marked the beginning of the oxygen revolution. Around 2.7 to 2.5 billion years ago, a group of microscopic organisms began tapping into the most abundant energy source Earth had ever known: sunlight. These organisms were cyanobacteria. Through photosynthesis, they used water and carbon dioxide to generate energy, and the byproduct was molecular oxygen. When oxygen combined with iron, it formed insoluble iron oxides that settled onto the seafloor, creating rock layers known as banded iron formations. These layers, concentrated between about 2.4 and 2.0 billion years ago, are direct evidence that Earth's oceans underwent a planet-wide phase of oxidation. As oxygen levels rose, vast numbers of ancient organisms that could not adapt disappeared. This is considered the first oxygen-driven mass extinction in Earth's history. Around 2.4 billion years ago, oxygen began to accumulate significantly in the atmosphere, marking what is known as the Great Oxidation Event. Oxygen concentrations were still low compared to modern levels, perhaps only a few percent of today's atmosphere, but even that was enough to change everything. The atmosphere shifted from a reducing state to an oxidizing one, triggering major changes in the carbon, sulfur, and methane cycles. Methane, a powerful greenhouse gas, was destroyed by oxygen, causing Earth's heat-trapping capacity to drop sharply. Oxygen made aerobic respiration possible, a way of extracting energy far more efficient than anaerobic pathways. From the same nutrient molecule, aerobic organisms could generate much more energy, allowing cells to grow larger, develop more complex structures, and eventually form multicellular life. Oxygen, once a destroyer, gradually became the foundation of complex life. The presence of oxygen in the upper atmosphere also led to the formation of the ozone layer, which absorbs much of the sun's ultraviolet radiation. Before this, the surface was nearly impossible to inhabit for long periods because of intense UV exposure. Taken as a whole, the oxygen revolution was not a single moment, but a process unfolding over hundreds of millions of years, marked by interruptions, feedback loops, and repeated rebalancing. And as methane disappeared from the atmosphere, global temperatures plunged. Earth moved closer to a state of near total freezing, a starkly opposite condition: cold, dark, and almost motionless. Geological evidence shows that Earth has passed through multiple periods of near global scale glaciation. These extreme ice ages occurred mainly during the proterozoic Eon, particularly between about 720 and 635 million years ago intervals, when ice may have stretched from the poles to near the equator. The cause did not come from a single shock, but from a dangerous chain of climate feedbacks. After oxygen levels rose sharply, methane was oxidized and rapidly depleted. Once ice began to expand, the albedo effect took hold. Ice reflects sunlight far more efficiently than land or ocean, causing the planet to absorb less energy and cool even further. At the same time, changes in plate tectonics pushed Earth deeper into crisis. The positioning of continents near the equator increased silicate rock weathering, a process that removed Cl from the atmosphere. As Cal became locked into rock, the greenhouse effect weakened even more. The result was oceans sealed beneath ice hundreds of meters thick, with some models estimating nearly 1 kilometer of ice in certain regions. Sunlight could no longer penetrate, and gas exchange between ocean and atmosphere nearly stopped. The carbon cycle was choked at the surface, and the planet appeared like a dead world, silent, frozen, and still. Beneath this ice, however, hydrothermal vents on the ocean floor continued to operate, supplying steady chemical energy. Cracks in the ice where faint light could slip through became microbial oases. Climate models suggest that Earth may have shifted from a snowball state to a much warmer condition in a relatively short geological time. Ice melted rapidly, sea levels rose, and vast amounts of nutrients, phosphates, iron, and minerals were released into the oceans. As the ice retreated, the oceans became richer in nutrients than ever before. While oxygen levels continued to rise, evolutionary pressures that had been building for millions of years suddenly erupted into biological innovation. Organisms that had survived in darkness now emerged into an open world where competition and diversification became the primary driving forces. And almost immediately after the final ice sheets withdrew, life returned and experimented with nearly every form imaginable. This was the Cambrian explosion, a moment when evolution accelerated in a way never before seen in Earth's history. The oceans were released. The climate gradually warmed, oxygen continued to accumulate, and biological, geological, and chemical cycles began operating at a different pace. Around 541 million years ago, within just 20 to 30 million years, the fossil record shows a sudden and unprecedented increase in biodiversity. Nearly all major animal phyla known today appeared, from arthropods and mollusks to segmented worms and early ancestors of vertebrates. One of the most important changes was the emergence of hard structures, mineralized shells, spines, teeth, and primitive skeletons. For the first time, organisms were not only surviving but building bodies like biological machines, capable of resisting damage, attacking, and moving efficiently. This completely transformed survival strategies. Before this, survival relied mainly on chemistry and physiology. From the Cambrian onward, body form itself became a weapon. The appearance of eyes was another revolutionary turning point, with fossil evidence showing that primitive visual systems emerged very early in the Cambrian. Species that swam faster, burrowed deeper, had harder shells, or faster reflexes gained the advantage. Notably, the Cambrian explosion also produced countless bizarre forms of life. Fossils from sites such as the Burgess Shale reveal organisms with completely unfamiliar body plans, multiple eyes, asymmetrical limbs, and shapes unlike any living species today. Most of these organisms went completely extinct, leaving no descendants. Why did the Cambrian occur at that moment, rather than earlier? Modern science points to a convergence of factors. Oxygen levels in the oceans and atmosphere reached thresholds high enough to support complex metabolism and larger bodies. Post-glacial oceans became rich in nutrients, driving the expansion of food chains. if just a few conditions had been different: lower oxygen, nutrient-poor oceans, or an earlier extinction. Biological history might have taken a completely different path. The Cambrian explosion reminds us that diversity does not equal durability. Many forms of life once existed but failed to survive later planetary changes. Yet it was precisely during this chaotic and creative period that the foundations of modern ecosystems were formed: complex food chains, differentiated ecological roles, and multi-layered biological interactions. As the oceans became crowded with competition and predation, a new pressure gradually emerged. Some organisms began turning their gaze away from the water toward a harsher, but more open environment. The Cambrian did not end the story of life. It pushed life to the threshold of an entirely new adventure. Around 470 to 450 million years ago, the first plants began to colonize land. They did not have tall, woody trunks like modern plants, but were non-vascular forms that clung close to the ground and lived near water sources. This innovation did more than allow plants to stand upright. It restructured Earth's entire surface. As plants spread, they began transforming bare rock into soil, retaining moisture, fixing carbon, and releasing oxygen. As a result, the atmosphere became increasingly rich in oxygen, surpassing the threshold needed to support large bodies. This set the stage for a remarkable phenomenon: the rise of giants. During the Devonian and Carboniferous periods, oxygen levels are estimated to have reached 30 to 35%, compared with about 21% today. With abundant oxygen, organisms that breathe through tracheal systems, especially insects, could reach unprecedented sizes. Fossils reveal ancient dragonflies with wingspans exceeding 70 cm, along with giant spiders and millipedes roaming dense forests. Animals, however, were the force that truly brought land to life. This transition began with fish, which evolved fleshy fins and primitive lungs to survive in shallow, oxygen-poor waters. From them emerged amphibians, creatures of two worlds, capable of breathing air, yet still dependent on water for reproduction. The solution emerged with the evolution of reptiles. With shelled eggs, water-resistant skin, and more efficient respiratory systems, reptiles broke free from dependence on moist environments. For the first time, vertebrates truly mastered life on land. They could migrate far from water sources, exploit new spaces, and diversify rapidly in form. Land transformed from a barren surface into a complex network of ecosystems where plants formed the foundation, insects served as intermediaries, and predators occupied the top of the food chain. During this period, ancient forests formed on a global scale. Woody plants flourished, accumulating enormous biomass. When they died and were buried under oxygen-poor conditions, some of that carbon did not return to the atmosphere, but became locked in sediments, eventually forming coal. The giants of the Carboniferous did not last forever. As oxygen levels declined and climates became drier, large body size turned into a disadvantage. As tectonic plates shifted, massive volcanic eruptions occurred, and climate fluctuated violently. The world of giants faced its most brutal challenge, and Earth entered a sequence of mass extinctions. Over the past 500 million years, Earth has experienced at least 5 major mass extinctions. The most severe occurred at the end of the Permian period, around 252 million years ago, commonly known as the Permian Triassic event. Geological evidence shows that approximately 90 to 96% of marine life and more than 70% of terrestrial species disappeared. But when previously dominant groups collapsed, ecological space opened on a global scale. And in that context, reptiles, organisms that had quietly adapted to dry and unstable environments, began to accelerate their evolutionary pace. Unlike amphibians, reptiles have water-resistant skin, protective shelled eggs, and physiological systems suited to harsh climates. These traits did not make the Permian Triassic catastrophe easier to survive, but they became decisive advantages in the post-extinction world hotter, drier, and more unstable. As forests declined and open landscapes expanded, reptiles did more than survive, they spread. This was followed by the Triassic and Jurassic periods, when reptilian lineages diversified rapidly. Some became bipedal predators. Others evolved into massive herbivores. Several branches adapted to life in the air or the oceans. This was the period when dinosaurs emerged and gradually came to dominate the land. They were not perfect organisms, but the result of millions of years of evolutionary experimentation in a post-catastrophe environment where the speed of adaptation mattered more than long-term stability. Notably, each mass extinction does more than eliminate life. It reshapes the direction of evolution that follows. Large size, efficient metabolism, or flexible reproductive strategies can all become keys to survival, but only for a limited time. As environments continue to change, those same advantages can turn into burdens. The Mesozoic era, often called the Age of Reptiles, was not a peaceful time. Although dinosaurs dominated for more than 160 million years, the planet remained in constant flux. Sea levels rose and fell. Climates oscillated. Continents drifted apart. Their dominance endured not because of stability, but because of an ability to withstand continuous change. From the very ashes of the dinosaurs, another path would emerge, a path leading to mammals and ultimately to humans. Around 66 million years ago, a brief moment brought an end to the era of creatures that had dominated Earth for more than 160 million years. After the Chicxulub impact, the sky darkened, the climate was thrown into chaos, and food webs collapsed. But as fine dust settled and sunlight returned, the planet entered a fundamentally different phase, a world left open, absent of giants. Throughout the Mesozoic era, mammals were small, nocturnal creatures living in the ecological shadow of dinosaurs. Fossils show that most mammals at that time weighed less than a few hundred grams and survived through stealth, flexibility, and rapid reproduction. Within 10 to 15 million years after the impact, mammals underwent a powerful diversification from insect eaters and herbivores to carnivores, from burrowers and tree dwellers to coastal species. This was a slow but persistent expansion unfolding against a backdrop of climates and landscapes being reshaped. One key factor was the brain. Anatomical data show that many mammal groups began to gradually increase the ratio of brain size to body mass. A larger brain did not immediately mean intelligence, but it enabled behavioral flexibility, learning, and rapid adaptation to changing environments. At the same time, plate tectonics continued to reshape the planet. Continents drifted, new mountain ranges formed, ocean currents shifted, and regional climates changed. These changes created ecological mosaics, diverse environments existing side by side that promoted species divergence. Tropical forests, grasslands, temperate zones, and deserts expanded in turn, each presenting a different survival challenge. Mammals, with their ability to regulate body temperature and care for their young, proved especially well suited to these challenges. Around 7 to 6 million years ago, as Africa's climate became drier and forests fragmented, one branch of primate mammals began adapting to upright bipedal walking, which allowed longer distance vision, freed the hands for carrying food and tools, and reduced direct exposure to sunlight. Fossils show that brain size increased step by step, accompanied by significant biological costs, high energy demands, longer developmental periods, and slower reproduction. Without the extinction of the dinosaurs, would this path have existed at all? Our existence, therefore, is not an inevitable result of evolution, but a fragile product of a chain of chance events, stretching across tens of millions of years. Journeying backward through time into Earth's prehistoric past, is not simply an exercise in reconstructing a world of molten rock, toxic atmospheres, or long-extinct entities from the quiet primordial oceans, where the first photosynthetic bacteria silently released oxygen and completely reshaped the planet's chemical balance, to the rise and fall of colossal species that once dominated the continents. That past has been permanently etched into every layer of sediment and every fossilized skeleton buried deep within the earth. These geological records are living diaries, bearing witness to an unchanging rule. Life always finds a path through even the harshest upheavals of the planet. Understanding prehistoric Earth allows us to recognize that humanity's existence today is not a given, but the result of a chain of chance events and extraordinary acts of adaptation by life over millions of millennia. By looking into that distant past, we not only uncover answers about our own origins, but also come to understand the fragility and immense value of the ecosystems we inhabit today. In the end, the journey into the past becomes the only true key to seeing the present clearly and accurately anticipating future scenarios, helping humanity protect the delicate balance of our one and only shared home in the vast universe. Thank you for staying with Woo Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.